Movement of a satellite follow differential equation 2 over e to the power of 3x times dy dx minus 3x minus 4. Initially, the satellite is at position y equals to half when x equals to 0 on the radar. Determine the next few positions of the satellite at x equals to 0.25, x equals to 0.5, x equals to 0.75, and x equals to 1 using second order Taylor series method. So let's try to answer this question, guys. So we have our initial problem. Just write down here initial position if you like. Initial position of the object, in this case satellite, at x equals to 0 is half. And given our differential equation to be 2 over e to the 3x, which we can rearrange. Okay, so let's just write down 2 over e to the power of 3x times dy dx equals to 3x plus 4. Therefore our dy dx equals to, you can say, e to the power of 3x times 3x plus 4 over 2, or half. And we given our initial condition, our initial value position in this case. Therefore this is our y prime, by the way. Y prime equals to dy dx, and our initial condition is x equals to 0, the value of y equals to half. So we can determine, or we can calculate the value of y prime to be at x equals to 0, e to the power of 3 times 0 over 2 times 3 times 0 plus 4. So in this case our value of y prime is half times 4 equals to 2. That's our y prime value equals to 2. And then from here we can work out our y double prime. Y double prime, which is basically the derivative of that. So we can write down like this as a product rule: e to the power of 3x multiplied by 3x plus 4. So this is equals to the first derivative of the first term is 3 e to the 3x multiplied by the second terms 3x plus 4 plus the derivative of the second term will be 3 times the first term, which is e to the 3x, so our y prime equals to half. We can take 3 and e to the 3x, so we can take both of them, so become 3 over 2. 3 over 2 times e to the 3x plus 4 plus 1, so equals to 3 over 2 e to the 3x plus 5. and the value of y prime, let's just write down here, y prime at x equals to naught is 3 over 2 e to the 3 times naught, 3 times naught plus 5 equals to 3 over 2 times 1 0 plus 5 times 15. So this is equals to sorry, this is 5. So this is simply be 15 over 2 as our y prime. Because the equation is only mentioning up to the second order of Taylor's method, so we can stop here. Okay. We can stop here and then directly the value of Taylor's, the coefficient of our Taylor's series up to the second order. So y naught plus x minus x naught over 1 factorial times this is to the power of 1 y naught 1 prime plus x minus x naught raised to the power of 2 to the power of divided by 2 factorial times y naught double prime, and that's it. And the value of y naught, as you can see in the equation, y naught equals to half, given here. So in this case y naught equals to half, x naught equals to 0, so we have only x times y prime, y naught prime equals to 2 over 1 plus x naught equals to 0 and y naught double prime equals to 15 over 2. So 15 over 2 times 2 factorial times x and y prime, okay, x squared. So we have overall our Taylor's equals to half plus 2x plus 15 over 4 x squared as the equation of our Taylor's. So let me highlight the things here. That's our Taylor series at up to the second order. So now we can determine the position of the object at x equals to 0.5, sorry, x equals to 0.25, 0.5, 0.75 and 1. So we can start with x equals to 0.25 equals to half plus 2 times 0.25 plus 15 over 4 times 0.25 square to be our calculator, half plus 2 times 0.25 equals to half plus 15 over 4 times 0.25 square equals to 1.2343 2344 and then our y equals to 0.5 square This should give us this mode. Just replacing. This is become 2 times 0.5 equals to 1 basically. This is equal to 2.4375. 2.4375, and at y equals to 0.75, half, then write down plus 2 times 0.75 plus 15/4 times 0.75 cubes. Then this one will become 1.5. .109, and finally at y equals to 1, the value is half plus 2 plus 15/1. This gives us 6.25 as the answer. So those are the answer. Three, 4. Yep, that's it.